The V-1 flying bomb and the V-2 rocket. You asked for them, so today we take them apart. Both weapons carried the letter V in their name, short for Vergeltungswaffe, which translates from German as revenge weapon or retaliation weapon. That wasn't an engineering label. It was propaganda, applied by Joseph Goebbels and the Nazi propaganda ministry to frame these machines as payback for Allied bombing of German cities. The engineers who built them never used that name. They had their own names, and every single one tells you something about what you're actually looking at. So before we pull a single panel off either machine, let's deal with the designations, all of them. The V-1 was officially designated Fieseler Fi 103 by the Reich Air Ministry, the RLM, which maintained a standardized numbering system for all German aircraft. Fieseler identifies the manufacturer, Gerhard Fieseler Werke GmbH, an aircraft company in Kassel. Fi is the RLM's abbreviation for that firm, and 103 was its assigned production number. The engineer who designed the airframe was Robert Lusser. But the program also carried a cover name meant to disguise its true purpose. FZG 76, short for Flakzielgerät 76, Anti-Aircraft Target Device 76. Anyone who stumbled across that paperwork would assume they were reading about a target drone for gunnery practice, not a flying bomb aimed at London. The project even had an internal codename, Kirschkern, meaning cherry stone, assigned when it was formally approved on June 19, 1942. So the same machine was simultaneously a cherry stone, a target drone, aircraft number 103, and a revenge weapon, each name serving a different institutional purpose. The V-2 was called the Aggregate 4, or A4, during development. Aggregate translates roughly as unit or assembly, and it was the series name for the entire experimental rocket program at the Peenemünde Army Research Center on the Baltic coast. The A1 came first in 1933, never flew successfully. The A2 followed in 1934, 2 successful flights from the island of Borkum that December. The A3, tested from 1937, suffered guidance failures. The team then built the A5, a smaller test vehicle used specifically to validate the guidance and control systems they'd need for the full-scale weapon. And the A4 was the culmination, 4th major design concept in a decade-long program. First successful flight, October 3, 1942. It reached 80 kilometers altitude and 190 kilometers downrange. The Vergeltungswaffe 2 label came later, applied only when the weapon entered operational use. The people who built it always called it the A4. The pulsejet engine powering the V-1 was designed by Fritz Goslau at Argus Motoren in Berlin, and it was the marriage of Goslau's engine to Lusser's airframe, initiated when Lusser visited Argus on February 27, 1942, that created the weapon the world would know as the buzz bomb. The V-2 program was led by Werner von Braun as technical director, just 30 years old when his A4 first flew successfully. These were parallel programs, one Air Ministry, one Army Ordnance, that shared a test site and, eventually, a propaganda label. The V-1 first struck London on June 13, 1944. The V-2 first struck Paris and London on September 8, 1944. Now, let's go inside. We start with the V-1. The engine that powered it was the Argus AS-014 pulsejet, and it's one of the simplest jet propulsion systems ever mass-produced. Compare it mentally to the turbojet engines appearing on the Me-262 at the same time. Spinning compressors, turbine blades, precision bearings, thousands of machined parts. The Argus pulsejet has none of that. Zero rotating machinery. It is, at its mechanical core, a hollow steel tube roughly 3.5 meters long, with a grid of spring steel reed valves at the front, fuel injectors in the middle, and an open exhaust at the back. A tube with flapper valves. That's the entire engine concept. Here's how it works. At the forward end sits the intake shutter grid, a lattice of thin spring steel flaps, each hinged along one edge. Between combustion pulses, the pressure inside the tube drops below atmospheric. That pressure difference pushes the reed valves open. Air rushes in. As it enters, fuel, standard 80-octane gasoline, sprays into the chamber through injection nozzles. A spark plug ignites the mixture. The combustion produces a violent pressure spike that slams every reed valve shut, sealing the front of the engine. With nowhere else to go, the expanding gases blast out the tailpipe, producing thrust. As the exhaust exits, internal pressure drops again. The valves spring open. Fresh air floods in, and the whole cycle repeats. 45 to 50 times per second. That frequency is the sound, the low, throbbing buzz that earned the V1 its nickname among Londoners, the buzz bomb, the doodlebug. Each pulse was a small explosion, and 50 of them every second produced a resonant drone audible for miles. Not a design feature, just an inescapable mechanical consequence of the combustion rate. The engine generated roughly 2.9 kilonewtons of thrust, about 660 pounds force, and sat mounted above the rear fuselage on a steel pylon, keeping the hot exhaust clear of the airframe and the intake positioned in clean airflow. One thing the pulsejet couldn't do was start itself. The reed valve cycle needs airflow entering the intake at sufficient speed to initiate combustion. For catapult launches, compressed air was injected into the engine during the launch sequence to kick off the first combustion cycles. For air-launched variants, dropped from Heinkel HE-111 bombers, the carrier aircraft's forward speed provided that initial airflow. Once the first few pulses fired, the engine was self-sustaining. Each exhaust cycle created the low-pressure condition that pulled in air for the next one, and the process continued until the fuel was gone. And here's what made this engine matter strategically. It was absurdly cheap and simple to manufacture. No precision turbine blades to machine, no bearings to balance. The reed valves were stamped spring steel. The combustion tube was welded sheet metal. The entire engine could be built with tools and skills available in any modest metalworking shop. That simplicity was the whole point. You didn't need to build a good engine, you needed to build thousands of disposable ones. But those stamped reed valves had a finite life, the steel flexing open and shut 50 times a second, absorbing combustion shock each cycle. It didn't matter. The V1 only needed to fly long enough to reach London from the Pas-de-Calais coast, and the valves were designed to last exactly that long. Engineered disposability. The airframe wrapped around that engine was built to the same philosophy. The fuselage was welded sheet steel, crude by aircraft standards, designed above everything else for production speed. Later variants used plywood wings when metal ran short. Overall dimensions, 7.7 meters long, wingspan of 5.4 meters, loaded weight of 2,150 kilograms. From nose to tail, the internal layout reads in a clean sequence that the 3D camera can trace in one continuous pass. Warhead in the nose, fuel tank in the mid-fuselage carrying 570 litres of 80-octane gasoline, compressed air spheres aft of the tank, then the autopilot and guidance compartment, with the Argus pulsejet sitting on its pylon above the tail section. Control surfaces, elevators and rudder, were driven by pneumatic servos powered by those compressed air bottles. No hydraulics, no electric motors. Just pre-charged steel spheres metering high-pressure air through small piston actuators that physically moved the control surfaces in response to commands from the autopilot. A closed system with a finite air supply, enough to last the flight and not a cubic centimetre more. Over 30,000 V1s were manufactured at facilities including the Volkswagen plant at Fallersleben and the Mittelwerk underground factory in the Harz Mountains. 2 parallel tunnels, each nearly 2 kilometres long, carved into the Konstein mountain near Nordhausen. The labour force came from the Mittelbau-Dora concentration camp. Prisoners assembled these weapons under starvation, exhaustion, and systematic brutality. The finished unit cost 5,090 Reichsmarks. That figure covered materials. It didn't account for the lives consumed in production. Now, guidance. This is where the V1 gets genuinely fascinating as an engineering artifact. The autopilot, built by Askania in Berlin, used 2 gyroscopes for stabilization. One held heading reference, azimuth, preventing the weapon from yawing off course. The second maintained pitch and roll stability, keeping the V1 flying level. These were mechanical gyroscopes, spun up before launch and preset to the desired heading. And the autopilot continuously compared the weapon's actual attitude against those gyroscope references, sending correction signals to the pneumatic servos. A magnetic compass provided a secondary heading reference to back up the azimuth gyroscope over the flight duration. Gyroscopes drift over time, and the compass helped catch that drift before it accumulated into a meaningful course error. Altitude was maintained by a barometric altimeter, a pressure-sensing capsule calibrated before launch to hold a preset altitude, typically between 600 and 900 meters. If the V1 climbed or descended from that band, the pressure change triggered elevator corrections. Crude, effective enough. But the most ingenious piece sat right on the nose. A small, vaned propeller, the Abstandszeller, the distance counter, spinning freely in the airstream, mechanically linked to a revolution counter inside the fuselage. Before launch, the counter was preset to a specific number of revolutions, calculated to correspond to the air distance from launch site to target. Each turn of that little propeller represented a known increment of distance travelled through the air. When the count reached its preset value, the weapon had flown far enough. And that's when it dove. The dive mechanism deployed spoilers on the tailplane and locked the elevators into a down position, pitching the V1 into a steep descent. Fuel to the engine was cut. The buzzing stopped. Londoners learned to fear that silence. As long as you heard the drone overhead, the V1 was still in powered flight. When it went quiet, the engine had been cut and the weapon was already falling toward the ground somewhere nearby. A few seconds of silence, then detonation. No terminal guidance, no corrections, no ability to steer toward a specific aim point after the dive began. Once the counter triggered, the V1 was a ballistic object. Its circular error probably ran roughly 12 to 19 kilometers, meaning half of all V1s landed within that radius of the intended target. It could hit a city, not a building, not a bridge, a city. The warhead in the nose contained 850 kilograms of amatol, a mixture of TNT and ammonium nitrate, detonated by an electrical impact fuse backed up by a mechanical one for redundancy. Surface blast on contact. No penetration capability, no delayed detonation. Raw explosive force delivered wherever the little nose propeller said, "Here." Because the V1 flew at just 640 kilometers per hour at low altitude on a predictable straight-line course, it could be engaged by conventional defenses. Anti-aircraft guns, barrage balloons strung on cables across its flight path, even fighters fast enough to catch it, Tempests, Gloucester meteors, could chase it down and shoot it out of the sky. That interceptability wasn't a design flaw, it was an inherent consequence of being a subsonic, air-breathing, low-altitude weapon. The same engineering that made the V1 cheap and simple also made it slow and vulnerable. The launch itself used the Walter W R2.3 steam catapult, a 48-meter steel and concrete ramp angled upward at the end like a ski jump, with a slotted tube running its length. Inside the tube, a dumbbell-shaped piston connected to the V1's launch cradle through the slot. T-stoff, concentrated hydrogen peroxide, met Z-stoff, potassium permanganate solution, and the resulting chemical decomposition produced enormous volumes of high-pressure steam almost instantly. That steam drove the piston down the tube, accelerating the V1 from standstill to 400 kilometers per hour in 48 meters. At the end of the ramp, the cradle released, and the weapon was airborne with its pulsejet already firing. That's the V1, the world's first operational cruise missile. Now, the V2, a completely different order of machine. The rocket engine is where we spend our time, because this is the most consequential rocket engine ever built, not hyperbole. Every liquid-fueled rocket that has flown since, every Atlas, every Saturn, every Falcon, contains engineering principles that were first made to work in this combustion chamber. Start with the propellants. Fuel, a 75% ethanol solution, ethyl alcohol mixed with 25% water. Oxidizer, liquid oxygen or LOX. The water in the ethanol wasn't contamination or a cost-saving shortcut, it was deliberate. That water reduced combustion temperature inside the chamber to levels the steel walls could survive. Without it, the engine melted itself. With it, combustion ran hot enough for useful thrust, but cool enough to keep the hardware intact. Engineering compromise, not elegance. Getting those propellants into the combustion chamber required a turbopump, and this single component is worth examining in detail because the turbopump concept born here is still the beating heart of modern liquid rocketry. Picture a single shaft. On one end, a steam turbine. On the other end, two centrifugal pumps sitting side by side. The turbine was powered by yet another chemical reaction. Concentrated hydrogen peroxide, T-stoff, the same compound used in the V1's catapult, decomposed by passing it over a sodium permanganate catalyst, Z-stoff, producing superheated steam and oxygen that spun the turbine wheel at 3,800 RPM. The hydrogen peroxide was stored in its own dedicated tank inside the rocket, with its own pressurization system, a self-contained power source feeding the pumps that fed the engine. An engine within the engine. One of the two centrifugal pumps on that shared shaft fed ethanol to the combustion chamber at 58 kilograms per second. The other fed liquid oxygen at 72 kilograms per second. Combined flow, 130 kilograms of propellant per second pouring into the engine. The entire fuel and oxidizer load, thousands of litres, was consumed in roughly 65 seconds of burn. That's how fast these pumps were moving fluid. The combustion chamber itself was a pear-shaped steel vessel, wider at the top where injection occurred and narrowing toward the throat of the exhaust nozzle. At the injection head sat 18 pre-burner cups, Brennkammertopfer, arranged in a ring. Each cup received separate streams of ethanol and liquid oxygen, mixed them, and ignited the combination in a confined pre-combustion zone before the burning flow expanded downward into the main chamber volume below. This staged arrangement ensured thorough, stable mixing, critical when you're injecting 130 kilograms of propellant per second into a confined space and expecting it to burn evenly rather than detonate. And here's the detail that ties the whole engine together. Before the ethanol entered those 18 pre-burner cups to be combusted, it first took a detour. The fuel was routed from the turbopump through a double-walled jacket, a narrow channel sandwiched between the inner and outer walls of the combustion chamber and exhaust nozzle. As the ethanol flowed through this jacket, it absorbed heat radiating inward through the chamber walls, heat that would otherwise soften and melt the steel. The fuel got hotter, the walls got cooler. Then the now preheated ethanol exited the cooling jacket and entered the combustion chamber to burn. This is regenerative cooling. The fuel protects the engine on its way to being burned by the engine. It's elegant in a way that's almost circular. The propellant is simultaneously coolant and combustion fuel, doing two jobs in sequence. And it's used in virtually every high-performance liquid rocket engine flying today. From the Merlin engines on SpaceX's Falcon 9 to the RS-25s that powered the Space Shuttle. The V2 was the first operational rocket to make this work at scale. The exhaust exited through a de Laval nozzle, convergent-divergent in profile, meaning the channel narrowed to a tight throat and then widened into a flared bell shape. Physics dictates what happens here. The narrowing passage accelerates the exhaust gases to exactly the local speed of sound at the throat. Then, as the gases expand into the widening divergent section, they accelerate further, past the speed of sound, well into supersonic velocity, extracting maximum kinetic energy from the combustion products. The shape of that bell isn't decorative. It's thermodynamics made physical. Every rocket nozzle you've ever seen, from a Saturn V to a Starship Raptor, uses this same convergent-divergent geometry pioneered operationally in the A4. Engine output, 25 metric tons of thrust, 56,000 pounds force. Burn time, 65 seconds. Then, silence. Structurally, the V2 stood 14 meters tall, 46 feet, with a body diameter of 1.65 meters and a loaded weight of 12,500 kilograms. It was divided into four main sections from nose to tail. The warhead compartment at the top, containing 980 kilograms of amytol. Below it, the instrument and guidance section, packed with gyroscopes, accelerometers, the analog computing unit, and electrical buses. Then came the two propellant tanks, the ethanol tank forward, the liquid oxygen tank aft, which together made up the vast majority of the rocket's volume and mass. The tanks weren't separate containers sitting inside a fuselage. They were integral to the rocket's structure. Their walls were the fuselage. Thin sheet steel, carrying the structural loads of the airframe while simultaneously holding thousands of litres of propellant. At the bottom, the tail section housed the engine, the turbopump assembly, and four large external fins. Here's what's striking when you see the cross-section. Most of the rocket was fuel. That 980-kilogram warhead represented less than 8% of total loaded weight. The rest was propellant, plumbing, pumps, and the structure to hold it all together. This was an extraordinarily expensive way to deliver less than a ton of explosive to a target, and everyone involved knew it. But the V2 was never really an efficient weapon. It was a technology demonstrator wearing a warhead. The liquid oxygen created its own engineering headaches. LOX is a cryogenic fluid. It couldn't be loaded into the rocket and left sitting. It would boil off continuously, venting through a relief valve, shrinking the usable supply every minute the rocket sat on the pad. This meant fueling was a race against evaporation. The launch crew had to load the LOX, complete final preparations, and fire the rocket within a tight window before too much oxidizer boiled away to sustain the full 65-second burn. On a hot day, the timeline compressed even further. Every V2 launch was, in part, a logistics problem fought against thermodynamics. The guidance system is where the V2 becomes something more than a big rocket engine, something genuinely new. At its core sat the LEV-3 guidance platform, containing two Hohenstein gyroscopes, one for pitch stabilization, one for azimuth control. Before launch, the rocket was physically aimed at its target using surveyed coordinates. The Meilerwagen launch platform was oriented so the rocket pointed in the correct direction. Then the gyroscopes were spun up and carefully aligned to the target bearing. Once the gyroscopes reached operating speed and were locked to the correct heading, the system was autonomous. The gyroscopes fed continuous attitude data to the guidance system, which compared the rocket's actual orientation against the desired trajectory and generated correction commands. Those commands went simultaneously to two different steering systems. Inside the exhaust stream, 4 graphite vanes, Strahlruder, deflected the rocket exhaust to steer during powered flight. These vanes sat directly in the extreme temperatures of the exhaust torrent blasting from the nozzle. They eroded constantly, shedding material with every second of burn. They didn't need to last long, just 65 seconds, but they had to survive those 65 seconds without cracking apart, or the rocket went wherever physics took it. On the outside, 4 aerodynamic rudders mounted on the fins provided supplementary control as the rocket accelerated and the airflow over the fins increased. But the true innovation, the component that made this a ballistic missile rather than just a big unguided rocket, was the integrating accelerometer. This device measured the acceleration the rocket was experiencing and mathematically integrated it over time to calculate velocity. It didn't know where the rocket was. It didn't need to. It knew how fast the rocket was going. And when the rocket reached a precise, pre-calculated speed, the exact velocity that would produce a ballistic arc terminating at the target distance, the accelerometer triggered the Brennschluss signal. Engine cutoff. The fuel valves closed. Combustion ceased. From that instant forward, the rocket was governed by nothing but gravity and its own momentum. No more steering, no corrections, no guidance of any kind. Pure Newtonian mechanics. A heavy object following a parabolic trajectory through near vacuum, arcing up to the edge of space and falling back to Earth exactly where the laws of motion dictated it would land. The entire accuracy of the weapon depended on cutting the engine at precisely the right speed, at precisely the right angle. Get the Brennschluss timing wrong by even a fraction of a second, and the impact point shifted by kilometers. Accuracy with this system, a circular error probable of 5 to 17 kilometers, depending on range. Like the V1, a city weapon, not a precision strike tool. The flight profile traced a clean ballistic curve, and it's worth walking through because it shows you how every system worked in sequence. Launch began from the Meilerwagen, a mobile transporter erector that could move a V2 by road, raise it to vertical, and support fueling and checkout on a steel launch table at any clearing, any stretch of road, any patch of flat ground with overhead clearance. This mobility is why Allied bombers could never find and destroy V2 launch sites. There weren't any permanent sites to hit. Ignition. The turbopump spun up, propellants flooded the combustion chamber, and the engine developed its full 25 tons of thrust. The rocket lifted off its table. 4 seconds of vertical ascent. Then the guidance system initiated a programmed tilt, a gentle pitch maneuver rotating the rocket's nose toward the target azimuth, transitioning from vertical climb to an angled trajectory. 65 seconds of powered flight, accelerating the rocket to 1,600 meters per second, 3,580 miles per hour, nearly 5 times the speed of sound. Brennschluss at roughly 80 to 100 kilometers altitude. The engine went silent. The graphite veins, partially eroded, no longer mattered. The rocket coasted upward on residual momentum, arcing to an apogee of 80 to 90 kilometers, the edge of space, technically, before the ballistic trajectory curved it back toward Earth. Re-entry into the thickening atmosphere subjected the airframe to extreme aerodynamic heating and stress as it accelerated under gravity toward the target. It struck the ground at approximately 3,500 kilometers per hour, faster than Mach 3. Which means this: the V2 arrived before its own sound. There was no warning. No air raid siren could help because there was nothing to detect in time. The explosion came first, then the sound of the rocket's arrival, the sonic boom, the roar of displaced air, rolled in afterward, seconds after the warhead had already detonated. Unlike the V1, whose buzzing engine gave you seconds to react, the V2 gave nothing. That isn't drama. It's the mechanical consequence of supersonic ballistic re-entry. And it's why the V2 was fundamentally uninterceptable in 1944. No aircraft could catch it. No anti-aircraft gun could track it. The mobile Milewagen launchers meant there wasn't even a fixed installation to bomb. Total flight time for a 300-kilometer target, roughly 5 minutes. A city on the receiving end had no warning and no defense. The warhead, 980 kilograms of amatol, detonated on impact via a contact fuse. A significant blast, certainly. But here's the absurdity of the V2 as a weapon. 12,500 kilograms of rocket to deliver less than 1,000 kilograms of explosive. Most of the machine's mass was propellant that burned away in slightly over a minute. The warhead was almost an afterthought, bolted on top of what was really an experimental rocket program. Both machines were mass-produced at the Mittelwerk underground factory. 2 parallel tunnels, each nearly 2 kilometers long, carved into the Kornstein mountain near Nordhausen. The labor force was drawn from the Mittelbau-Dora concentration camp. More people died building V2 rockets than were killed by them. That fact belongs in any honest account of these machines, right next to the engineering. So how do these two weapons compare? Not as combat systems, as engineering. The V1 breathed air. Its pulsejet ingested atmosphere, mixed it with gasoline, and produced thrust through repeated combustion pulses. It could only fly where there was air to breathe, low altitude, inside the atmosphere. The V2 carried its own oxidizer, liquid oxygen stored on board. It didn't need the atmosphere at all, which is why it could fly to 90 kilometers altitude, to the edge of space, where there's essentially nothing to breathe. Speed, 640 kilometers per hour for the V1, subsonic, well within the reach of a Tempest. Approximately 3,500 kilometers per hour for the V2, over Mach 3. Complexity. The V1 was barely more complex than what it sounds like. Welded steel tube, flapper valves, pneumatic servos, a propeller on the nose, counting distance. The V2 contained over 20,000 individual components. Turbopumps, regenerative cooling circuits, inertial guidance platforms, an integrating accelerometer, an analog computing unit, graphite vanes operating in superheated exhaust. Cost: 5,090 Reichsmarks for a V1. Estimates for the V2 run to 100,000 Reichsmarks or higher, and that's before you account for the development infrastructure, the launch equipment, and the liquid oxygen production chain. One was cheap, simple, and interceptable. The other was ruinously expensive, staggeringly complex, and unstoppable. One was the world's first operational cruise missile, a pilotless aeroplane following a preset course through the atmosphere. The other was the world's first operational ballistic missile, a rocket that left the atmosphere entirely and fell back to Earth on a trajectory governed by nothing but physics. These aren't variations on a theme. They're fundamentally different weapon concepts that happen to share a letter. And both left descendants. The V1's lineage runs through every cruise missile in modern arsenals. The conceptual line from the Fi-103 to today's Tomahawk cruise missile, airframe, air-breathing engine, autonomous navigation, low-altitude flight to a target, is direct and traceable, even though the technology evolved beyond recognition along the way. The V2's legacy runs deeper still. Under Operation Paperclip, von Braun and over 100 of his engineers transferred to the United States, eventually continuing rocket development at Fort Bliss, and later at the Army Ballistic Missile Agency in Huntsville, Alabama. They brought captured V2 rockets, components, and documentation. From that foundation came the Redstone missile, a direct descendant of the A4, then Jupiter, then the Saturn V that carried Apollo astronauts to the Moon. The Soviets captured their own V2 components and engineers, and their R1 missile was a near-exact copy of the A4. That R1 led to the R2, the R5, and eventually the R7, the rocket that launched Sputnik in 1957 and Yuri Gagarin in 1961. Both superpowers' space programs grew from the same root, planted on a Baltic island in the 1930s. But beyond lineages of specific rockets, what persists are the engineering principles themselves. The turbopump, using a small, independently powered turbine to force propellants into a combustion chamber at flow rates no pressure-fed system could match. Regenerative cooling, running fuel through the engine walls before burning it. Inertial guidance, navigating by gyroscopes and accelerometers with no external reference. The Delaval nozzle, shaping the exhaust path to accelerate gases past the speed of sound. Every one of those concepts working together for the first time on October 3, 1942, on a test stand at Peenemünde, is inside every orbital rocket that flies today. Not as heritage, as living, working engineering. That's what you see when you look inside these two machines. Not just weapons from 1944, the mechanical foundation of everything that came after. If you want more breakdowns like this one, subscribe. We'll keep taking things apart.